Greetings, Mr. Burkhart. Here to talk to you about this week's lab. Following this clip, you will see me demonstrate the lab for you and share the data with you. So we've got a couple of pictures here. Be really helpful if you watch the Khan Academy videos for the week first. Those people are doing a really good job of explaining harmonics, resonance, and why you only get certain frequencies to resonate in tubes and on strings. I watched the videos. I thought they did a really good job. I really think it would bear repeating for me, though I'd be glad to hang out with people in a Zoom or a Google Meet or whatever and talk about things you don't understand. So the top picture is showing you a tuning fork resonating air in a pipe. So you can see that's what's happening physically as the air is being agitated, and you get these compressions and rarefactions. Another way to model that wave is the picture on the left, which is showing you how the air is being, they've modeled that in the video, and they show you why that model works. And you can see that there we have a wave coming in, and then there's a node because it's not going to move when it hits the water at the bottom of. So this is basically a pipe with water in it that we're using. We're going to have a pipe that's submerged in water, and we're going to lift the pipe out of the water, and we're going to hold a tuning fork over it, and we're going to figure out where the spot is where the tuning fork will resonate and hum. It'll be really loud, and if we know that spot, we can use that to do different things. Back in the day, we used to calculate the speed of sound because there wasn't any way really I could hide the identity of the tuning forks from the students. So we found the wavelength and we found the frequency. We're not doing that in this lab. I thought it may be a more clever thing to do, since we all know what the speed of sound is anyways, or we should know that it's about 343 meters per second. That I could make this a lab where the tuning fork frequencies could be a mystery to you, and you would have to try to determine their identity. So that's what you're going to do. You're going to watch me ring a tuning fork over some tubes and lift the tubes out of the water until they harmonize or they resonate, and then we'll use that length of pipe. So basically, once we know how long the pipe is that's resonating, we know from watching the Khan Academy videos that the length of a pipe that's got water on one end, that's just blocked, not open on both ends. So there's open on both ends is different, but if it's blocked on the bottom, it's a fourth of the wavelength. So 4 times the length of the pipe is equal to wavelength, long story short. If we know the wavelength and we know the speed of sound in air, we should be able to calculate the frequency of the tuning fork. And that's what I want you to do. This lab is not going to be due for a couple of weeks. I want to give you a week to work on it, and then it'll be due the following week, because in class, we're going to do the percent error together in class. The second week, I'm going to give you the identities of the tuning forks so you can see how close you got, and then we can work out what your mistakes might have been. You should be able to get, well, if you could actually see the numbers really clearly yourself. I know that it was hard for me to get the camera completely focused down there in the tube. And so there's going to be some error, and you're going to have to do the best you can to figure out what that distance is. And I did kind of call out roughly what they were to give you an idea so that you could kind of estimate. All right, so that's what we're doing for the lab. Thank you. Good luck.